Section 3.11. In this section, we briefly discuss an application of the type of differential equations we've been analyzing in this chapter. As you know, our differential equations have been second order, linear, constant coefficient, and we have dealt with differential equations that are both homogeneous and non-homogeneous. This family of differential equations serves as a model for a pretty broad range of physical phenomena. In this section, we're going to look at a single example of a context that can be modeled by this type of differential equation, namely a mass on a spring. This is a context we've actually discussed earlier in the semester. If you go back to section 2.7, I provided an explanation of the derivation of the differential equation that would model the location or displacement of the mass when it's attached to a spring and then that spring is attached to some support. In that derivation, we utilized Hooke's law, Newton's second law, etc. If you don't quite remember the setup, I would encourage you to go back to section 2.7 and take a look at the notes that I provided there. But for now, I'm going to trust that this equation that I've labeled equation 1 here represents exactly what I've just described. It represents the displacement or location of the mass, which I'm using x to represent. And that displacement or location is changing with respect to time. So that function x is determined by this differential equation. Here the constants indicate familiar aspects of the situation. M is the mass. Lambda, this constant here, is the coefficient of friction. And K is the spring constant. G of t is any force that I apply externally to the system. So I think of this as a force that I apply to the mass itself, or possibly a force I apply to the structure, the support, which is holding the spring. This is, of course, exactly the type of differential equation we've been dealing with this entire chapter. It is linear, it's second order. My coefficients on the left are all constants, and there will be many cases in which the external forcing function is 0. That'll lead to a homogeneous differential equation, and we'll also investigate cases where there exists some non-zero forcing function. That is, we'll be investigating non-homogeneous versions of this differential equation as well. But all of the techniques that we've used so far, defining the characteristic polynomial, identifying the roots of that characteristic polynomial, building the general solution. In addition, the two techniques for solving non-homogeneous differential equations that we've discussed, undetermined coefficients, variation of parameters, all of those techniques, everything we've done from this chapter can be applied to differential equations of this form. And so we'll be able to use all of our techniques from this chapter to provide a pretty robust description of the types of behavior we can expect from the mass. Before we look at an example, I just point out here in this paragraph that while we will be limiting ourselves in this section to just be focusing on a mass spring system, behavior which is oscillatory or wave-like is very common in lots and lots of different physical contexts. So as I said, our focus in this section will be a mass spring system, but the techniques and the methodology that we will utilize can be applied in lots and lots of different contexts. So let's start with a specific example, and then I'm actually going to spend the majority of this lecture just discussing general cases and kind of investigating as efficiently as possible lots and lots of different general possibilities for the types of behavior that can occur in this one context. So example 1 gives us a specific case to look at. We have a mass, which we're told has 0.5 units, and that mass is attached to a spring, and the spring constant is 1/2. I have intentionally left off specific units such as kilograms for the mass, just to kind of clean up the calculations. As you see these problems in textbooks or in other contexts, there will be units attached here, but for the purposes of this first example, I just wanted to keep it as clean as possible. We're told additionally that there's a dampener on the motion of the mass, and that effectively introduces a coefficient of friction of 0.0625. And for this first example, I'm going to assume there is no outside force acting on the system. In this green box, I've provided us with a reminder of the structure of the differential equation that we'll be using throughout this entire lecture. And within that differential equation, there are essentially 4 parameters. Give myself a little list to fill in over here based on the information that's been provided in the problem. In rereading the problem, I'm able to pretty quickly identify these parameters. I'm told that the mass is 0.5 units. The coefficient of friction, which is this lambda variable, we're told is effectively 0.0625. The spring constant, which is represented as K, is 1/2. So I've got that here as 0.5. And then since there is no outside force acting on the system, I have forced GFT to equal 0. This leads directly to a second order homogeneous LHCC differential equation, which is exactly the type of problem we've been dealing with for the last several sections. So once I've got it set up, I should be able to find the general solution pretty directly. Here I've used the quadratic formula to find the roots of my characteristic polynomial. A little messy, and we have ended up with complex roots, but that's okay. Let me go ahead and use these roots to build my general solution. This is a process that we're quite familiar with by now. Here I've taken my complex roots, identified these 2 components, and then filled them into the formula appropriately to build this solution. Sorry, I'm a little used to dealing with non-homogeneous equations recently, so I felt like I needed to label this as y sub h, but this is of course just the general solution. This is the whole equation that I'm dealing with in this particular case. In part B, we're going to be given additional information that will allow us to define and incorporate initial conditions. We're told, for example, that the mass is released from an initial positive displacement of 2 units. I can capture that property by defining x of 0 to equal 0. I just realized I think I wrote y as the dependent variable in the previous part. So maybe I'll go back and fix that, but we are dealing with x as my dependent variable, x representing displacement or position. Anyways, I'm looking for a second initial condition in my statement of this problem, and it's kind of hidden a little bit. It actually tells me that the mass is released. So I can picture pulling the mass to a positive displacement and then simply letting go. So when I initiate the movement of the mass, I'm not pushing the mass at all, either positively or negatively. So if you think about it, that indicates that I'm going to have an initial velocity of 0. So I'm going to displace the mass, I'm going to stretch the spring out, and then I'm not going to introduce an additional initial velocity. I'm simply going to release the mass, which means I'll have this initial velocity of 0. And then I just realized that I have a typo here as well. I'm told that the initial displacement should be 2 units. Incorporating initial conditions is something we've done quite a bit, so I'm going to breeze through these details pretty quickly. Incorporating those initial conditions, I believe I get C1 equals 0 and C2 equals 2. Plugging in those coefficients gives me a solution that I've got in a blue box here. And if I think about the nature of this solution, it's pretty intuitive. This is a relatively poor sketch, but it captures the qualitative nature of this solution because I have a trig function, specifically cosine, that's being multiplied by a decaying or decreasing exponential. So this 2 times this exponential effectively acts as the amplitude of this trig function. If we dig a little bit further, we said that we have an initial displacement of positive 2, but that we have no initial velocity. We can actually kind of see that in the graph. I start at t equals 0 with a displacement of 2, and then the mass immediately tries to return to equilibrium. I've stretched it out 2 units, and then once I let go, it immediately pulls back toward the center. Remember that this graph is, of course, with respect to time, so the actual oscillation of the mass would be in 2 dimensions, just down and up. Sorry, I guess that would be 1 dimension, it should be down and up. The mass itself is not moving to the right in any sense, but if we plot the displacement with respect to time, we see this graph. We're asked to identify some features of this trigonometric behavior or this oscillatory behavior. Specifically, we're asked to state the period. This isn't steady oscillation, it is decreasing oscillation. And so technically this is not exactly a periodic function, but I know that the cosine part of this function is going to lead this function to repeat itself in some sense. It's not perfectly repeating itself because the amplitude is decreasing with respect to time. So that's why I call this a quasi-period. And you remember from dealing with trig functions in the past that to identify the period of sine or cosine, I take 2 pi and divide by whatever the coefficient on t is. In this case, square root of 255 over 16. And simplifying that a little bit, I get an estimate here of 6.2955 seconds or minutes or whatever the units on time are. And so in my picture, that represents the length of time required to get back to a peak. Again, this isn't perfect oscillation, so I can't say that the function is exactly repeating itself because the amplitude has decreased, but at the same time, it feels pretty periodic. So that's why we do apply this type of terminology. You'll also recall that period, frequency, and wavelength are all different sides of the same coin is how I think about it. So in this particular case, I've asked to identify period, but I could easily modify these calculations to identify the wavelength or the frequency as well. This solution makes sense intuitively because if I have a mass on a spring, I expect some sort of oscillation or oscillatory behavior. But remember that this type of solution where I have complex roots to my characteristic polynomial is only one of 3 possible cases. So what I'd like to do next, I'd like to look more generally at what could possibly happen in this context. So my goal is to categorize all possible solutions of this ODE that we're looking at right now. And I mean all possible. I want to do this as broadly as I can. An important thing to note as we get started is that based on the physical quantities that these coefficients represent, it's reasonable to assume that m, lambda, and k are all positive, and only lambda could potentially be 0. If m were to equal 0, then I wouldn't have a mass, and so the problem wouldn't be well defined. Similarly, if k were to equal 0, then I wouldn't have a spring, and so m and k have to be non-zero. Lambda equals 0 represents a kind of special case, sort of idealized case where there is no friction. But otherwise, I think it's reasonable to assume that all 3 of these coefficients must be positive. So let's start by looking at the general characteristic polynomial. And since I'm not going to specify particular values for m, lambda, or k, I don't really have any hope of trying to factor this. So I have to rely simply on using the quadratic formula to solve for the roots of this characteristic polynomial. So here's that expression based on the quadratic formula for the roots of my characteristic polynomial. And this expression is actually really key to delineating the different cases that could potentially occur. And we've seen a few problems on homework and quizzes and tests and stuff that ask us to identify the different cases, and those always revolve around the value of this expression underneath the square root. And so the 3 potential cases that we'll get here all hinge on what happens underneath the square root. What happens with this expression here? This is called the discriminant. And the value of this quantity, lambda squared minus 4mk, will determine if I have a real repeated root, real distinct roots, or complex roots. Let's spell out each of those cases and explore a few properties of solutions in each case. So in the first case, if lambda squared minus 4mk is greater than 0, then this expression of the square root will be positive. Therefore, I'll have 2 real distinct roots to the characteristic polynomial. I could call those, let's say, R1 and R2. Here I've written them out explicitly, and this expression is a little intense, but I've got some coefficient times t in the exponent, and that was generated by using the minus here, and then the similar expression over here, but with the plus. So I know that in this case, I'll have 2 exponential functions that build my general solution. Are there more details that I can add? Looking at this expression here, now bear in mind all of the variables, I guess the parameters, sorry, lambda, m, k, we determined that those are all positive. So if I look at this expression, I've got a negative minus something. So it's clear that this expression is going to be negative. In this second expression, there's the possibility that this numerator could turn out to be positive, but I've done a little work over here on the right to verify that this numerator is always negative. Since the denominator is positive, then overall this fraction is always negative. So in general, when I'm solving this type of LHCC differential equation, I could end up with positive values in the exponent, which would lead the solutions to grow without bound. But in this particular case, since all of the coefficients involved are positive, I can safely conclude that these two quantities are both negative. Therefore, both of these exponentials are decreasing. Therefore, the limit of every solution of this form will be 0 as t grows without bound. Let's take a look at another case. Another possibility is that the discriminant equals 0. In that case, this entire square root term will go away, and so my r value will simply be negative lambda over 2m. That means I'll have a single real repeated root. So I can use techniques from earlier in the chapter to build the general solution in this case. It's easier to see in this example that the coefficients in the exponent are both negative, so both of the exponential terms will be decreasing. But the distinguishing factor in this case is that I've got this t. So while the exponential terms are both heading towards 0, for small t values, this t will dominate, and it'll actually lead solutions in this case to have a single critical point. Here's a rough sketch of the type of behavior that I'm trying to describe. Whereas in the previous case, my solutions are all heading towards 0. In this case, for small t values, this linear term actually dominates, and it causes the function to grow away from 0 before the exponential term takes over, and then it returns back to equilibrium. In the physical context that we're trying to model, this is equivalent to my mass. Starting with some initial displacement, it looks like I pushed it away, and it went away from equilibrium initially, but then it pulled back and settled in towards equilibrium. So while it is still true that the solutions in this form will have a limiting value of 0, what distinguishes this case is that these solutions will have one critical point. The third and last case will occur when lambda squared minus 4mk is less than 0, and that will of course lead this expression to be negative, which will lead me to have imaginary or complex solutions to my characteristic polynomial. So of course, in this third case, when I have complex roots, I build my solution in this way. Again, it's a little crazy to write this all out explicitly, but all of this is given to me in the quadratic formula. So I feel like it's reasonable to include it here in the general solution. Once again, we note that this exponent is definitely negative because lambda and m are both positive. So this will only lead to decreasing oscillation. And then this coefficient on t, as we saw in the previous example, can be used to determine the period or quasi-period of this oscillation. So all other sort of periodic properties, wavelength, frequency, can all be derived based on this expression here. So that is a full, exhaustive summary of the different types of behavior that can occur in this context. I don't know, for me personally, it feels like there could be so many different possibilities, and yet because of the structure of the roots of the characteristic polynomial, we can definitively say that there really are only these three qualitatively distinct cases. So at least for the homogeneous differential equation, that is, when there's no external forcing function, these three cases exhaustively describe all of the possibilities for the behavior of the mass on the spring. Some terminology that's commonly associated with these three cases has to do with how much oscillation the system experiences. If we scroll back up to our first case, We said that in the first case, solutions simply tend toward equilibrium. They exponentially approach equilibrium. And so in that case, it feels like the dampening is too strong. There's no oscillation whatsoever. So that situation is often described as over-damped. Sort of on the other end of the spectrum is our third case, where we've got lots of oscillation, as indicated by the sine and cosine functions. So there's some initial displacement of the mass, and then the oscillation continues for a long period of time. In a certain sense, that feels like there's not enough dampening in the system. And so this case is often called underdamped. That leaves this middle case where we have, in a sense, one oscillation. We have one critical point, so functions either increase out past their initial displacement or potentially pass through equilibrium once and then return to equilibrium. So in a sense, this is thought of as being the perfect amount of dampening. So this is called critically damped. So as I said, those three cases really do cover all of the possibilities for the behavior of a mass on a spring. Those are the cases in the homogeneous context when there's no outside forcing function. What I want to do next is look at a few specific cases when we have some outside function acting on the system. In these two paragraphs, I start by indicating that although in theory g of t, the function that describes the force acting externally on the system, could be basically any function, in reality there's a relatively small set of functions that could reasonably occur. I give an example of supposing, g of t equals e to the t. This would somehow indicate that there is a force being applied to the system that grows exponentially. That would mean that after just a couple seconds or minutes or whatever the time units are, the magnitude of that force would be extremely large. So I think that an increasing exponential function is not realistic as a candidate for a g of t in this context. In contrast, if I have a decreasing exponential, I think that might be reasonable because that would somehow indicate that there's a force exerted on the system that has some initial magnitude and then decreases to essentially zero pretty quickly. So in example 2, I want to investigate possibilities for what type of effect that type of function, a decreasing exponential function, could have on the behavior of this sort of system. Let me start by considering the case where the natural behavior of the system, that is, the solution that I would get if there was no forcing function, yields two real distinct roots to the characteristic polynomial. That would yield a solution to the homogeneous version with the two exponentials as I've got labeled here. Recall that, as we indicated above, both R1 and R2, as I've decided to name them here, would be negative. So now we'd like to suppose what would happen if the g of t in the non-homogeneous equation had the structure of an exponential of this form. In such a case, I would most likely apply undetermined coefficients, and I would select a y of p or y sub p that has the same basic structure as the g of t that we're supposing. Now, in most cases, my final solution would simply be the sum of the y sub h and y sub p that I have written here. And since I know that R1 and R2 and beta are all negative, I know that all three of the exponential functions that now appear in my general solution are all tending towards zero. Maybe there's something interesting going on in terms of the coefficients, and one is positive and maybe the others are negative, but generally speaking, the overall structure of this function is simply an exponential that is approaching zero. More specifically, the addition of this term that results from the forcing function doesn't qualitatively change the behavior of the system. But you'll recall that this structure for a general solution assumes that there is no repetition between the y sub p that I have chosen and either of the terms in my y sub h. That is to say, I'm assuming that beta is not exactly the same as either R1 or R2. What would happen if that wasn't the case? Let's suppose beta equals R1 or R2. Without loss of generality, I'll just assume that beta equals R1. And as you recall from our discussion of undetermined coefficients, that repetition would force me to modify my choice of y sub p. Specifically, I would have to multiply it by a t. So now my general solution would have this structure where this exponential term now has a t multiplied by it. It's still true that r1, r2, and beta are all negative, but introducing this t as a sort of coefficient on this exponential leads solutions to grow away from zero for small t values. To give a very rough sense of the behavior that I'm trying to describe, we would say that y now has a critical point, and I've drawn a very poor sketch here, where instead of the functions simply approaching zero, they actually have a critical point, in this case a minimum as I've drawn it, and then turn around and then approach zero. So this isn't a drastically different type of solution, but it is qualitatively different than the y sub h, the homogeneous or natural behavior of the system. And the catalyst for this different type of behavior was the fact that we had repetition between a term in the y sub p that I was proposing and a term in my y sub h. Let's consider another case. For example, if my characteristic polynomial has one real repeated root, I know that my homogeneous solution will have essentially this structure here. Once again, I've left out the exact expression for this r value, but I do know that r will be negative. And as we pointed out above, this solution is distinctive because it has a critical point. For small t values, it increases away from equilibrium, and then these exponentials drive the mass back toward equilibrium. In the case that we just considered, the most interesting thing happened when there was repetition. So let me consider the case here where the beta in my g of t exactly matches r. If my initial choice of a y sub p would simply be a e to the beta t, I know that that's not feasible because there's repetition between this exponential and this exponential. But even multiplying by a t isn't sufficient because there's still repetition between this t times exponential term and this t times exponential term. So I'd have to multiply by a t squared to finally eliminate the repetition between the y sub p that I'm proposing and all of the terms in my y sub h. With this y sub p, my general solution will now have this form. And what's distinctive in this case is that this type of function has two critical points. And while I admit this is not a drastically different type of function, it's nevertheless qualitatively different from the homogeneous or natural behavior of the system that we would observe if there was no forcing function. And I'd like to reiterate that the most interesting thing happens when there is repetition, when we see a term in my g of t that perfectly matches terms in my y sub h. That is to say, the external forcing function perfectly matches some aspect of the natural behavior of my system. The most interesting case of this happens when my external forcing function is sinusoidal, and that's what we look at in the next example. In example 3, I want to consider the potential influence of forcing functions that are trig functions on the system that we're considering. And I'd actually like to kind of cut to the chase and not consider several different cases. I'd like to sort of go straight to the most interesting case. And this most interesting case will demonstrate a phenomena called resonance. There are a lot of interesting applications or examples of resonance in physical contexts. And what I'd like to demonstrate through this example is the mathematical justification or confirmation of those phenomena. So I'm going to start by making a simplifying assumption. I'm going to assume that our system has no friction. In order to enact that assumption, I'll force lambda to equal 0, since lambda indicates the coefficient of friction. That simplifies my overall ODE to give me just this equation here. And now recall that m and k are both positive. Therefore, when I try to solve the characteristic equation, I will definitely end up with complex roots. Specifically, I'll get these two purely imaginary roots here. R is plus or minus the square root of k over m times I. That leads to a homogeneous solution of this form here. And this type of function is often described as steady oscillation because the exponential term that would typically be driving this oscillation towards equilibrium is absent. So in this case, we just have steady oscillation. So again, I would describe the behavior of the system as steadily oscillating without an increasing or decreasing amplitude. Which again intuitively makes sense because if I have eliminated friction, then if I displace the mass, I assume it'll just continue oscillating endlessly. So now we want to consider the effect of an external force that's either a sine or a cosine term. And what's key here, as we demonstrated in the previous example, is that the most interesting thing happens if this external forcing function matches the natural behavior of the system. So I'm going to assume the kappa, that's the coefficient on t in my forcing function, is exactly the same as the coefficient on t in the natural behavior of the system, as indicated by this homogeneous solution. Remember that these coefficients indicate periodic properties, such as wavelength, frequency. So you can kind of think of this as saying the external force is matching, perfectly matching, the frequency or wavelength or period of the natural behavior of the system. This is exactly the phenomena of resonance. There's some natural, it's often called like the natural frequency of the system, as indicated by square root of k over m, or some derivative, some quantity based off of that. And my external force is matching that natural frequency perfectly. So mathematically, what happens when this phenomena is present? Well, as we've seen with many examples, when there's repetition between one of the terms in the y sub p that I've chosen and one of the terms in the y sub h that indicates the natural behavior of the system, that y sub p is not sufficient. And the way that I remedy that repetition is to multiply that y sub p by t. This means that my y sub p will have to have this form here, and my general solution will have the form here. Now what's significant is that I still have the sinusoidal, the oscillatory behavior that the natural system demonstrated, but this t is acting like a magnifier, a scalar. It's acting like the amplitude on these trig functions. And so as time increases, whereas the natural behavior of the system demonstrates steady oscillation with no increase or decrease in the amplitude, these new terms out here on the end, introduced due to the forcing function, will have an increasing amplitude. Specifically, as time increases, the amplitude will increase linearly with time. So after 2 seconds, the amplitude will be twice as big. After 3 seconds, 3 times as big, etc. So this causes an otherwise steady system to grow without bound. So a system which naturally has bounded behavior now has unbounded behavior. And it's worth pointing out too that we made no mention of the amplitude of the forcing function. At no point did I indicate that g of t needed to have a really large magnitude. The magnitude, the amplitude of g of t was not significant. The only thing that was significant is that the frequency of g of t perfectly matched the natural behavior of the system. When that occurs, that leads to this phenomena of resonance, which turns a bounded system into an unbounded system. I always say my favorite example of this is when you were jumping on the trampoline with your little brother or sister, and your little brother or sister was jumping at some specific frequency, and you showed up and you started jumping. And so long as you and your little sibling were jumping at different frequencies, your amplitudes, how high you were jumping, was relatively unaffected. But if your timing was just right and you could make your frequency, your rate of jumping, perfectly match that of your little brother or sister, then their amplitude became unbounded. That's a bit of an exaggeration, but they double bounced, is what we used to call it when I was a kid. There are other examples of this in like more serious natural systems, but that's always the example that comes to my mind. So in this section, we were looking at an application of LHCC and non-homogeneous differential equations specifically to a mass spring system. But as I pointed out, there's lots and lots of other physical phenomena that can also be modeled by this family of differential equations. So as you move forward in engineering and physics courses, you'll see other contexts that have essentially this same structure. And so hopefully these examples that we've worked through give you some sense of the mathematical foundation that those models are built on.